Okay, so welcome to this afternoon's session, which is on named entity recognition. So the first of our natural language processing advanced sessions. So back in the first session on natural language processing, we did a lot around grammar, which I'm sure you found as fun as I did. And we talked about how we might approach named entity recognition and sentiment analysis, which are the two key things that I'll be showing you in this course around natural language processing. There's other stuff as well within that sort of broad umbrella, but these are two things that in particular are pretty useful. I note that in the HSMA projects we're taking forward, 4 of the projects have some form of natural language processing, whether it's named entity recognition or sentiment analysis or a bit of both within the project somewhere, either at the forefront or as a sort of key part of the rest of the project. So hopefully this will be really useful for you guys to see this. And before we sort of dive into me showing you how to do this stuff, which is actually pretty easy, at least at the first level, let's just have a quick recap of what we mean by named entity recognition, and why we might want to do this and how we might sort of find these named entities. So what do we mean by named entity? Named entities are real world objects that can be denoted with a proper name. So it might be physical objects, so things like Dan Chalk, University of Exeter, or it might have a more abstract existence, so things like discrete event simulation, or woodwork, which don't have a physical existence but are in abstract existence. They would also count as named entities too. And these things are the kind of thing that would be really useful to extract this sort of stuff out of free text data. And if you recall, we said that there are lots of different types of named entities, and it's useful being able to not only know what the named entities are, but also what type they are, because it might be, for example, that we want to look at some text and we're just interested in extracting the people that are mentioned. And if we can have a system where we predict what type of named entity it is, we can say, okay, well, I just want to grab the people from that. So that's why we do this. And there are different types depending on different packages that you use, but SpaCy is the most widely used, and that's the package I'm going to show you how to use today. And SpaCy has its own set of categories. We went through this list last time, things like people, nationalities, organizations, geopolitical entities, all that kind of stuff. I also explained that SpaCy allows you to add your own. So if you feel that there's a category that would better capture some of the named entities you're interested in, you can add that and teach it how to look for those kinds of things as well. It's really powerful. Now, we also talked about noun phrases. We said how noun phrases are phrases that are either headed by a noun or an indefinite pronoun, and perform the same grammatical function as a noun. So put another way, a noun phrase is basically a noun along with the things that modify that noun to identify it. So my cat being the noun, and which cat is it? It's my cat. John's cat identifies cat as the noun, and it's John's cat. It's the cat with white stripes. It's the cat who ate all the tuna. Sounds a lot like my cat. But that's basically, these are examples of noun phrases where you've got a noun and the things that modify and describe that noun to identify it. So we also then talked about definite noun phrases, which is a noun phrase where the head noun clearly refers to something specific, something that the reader has been introduced to before within the text. So to find these, we identify where the head noun is prefaced by the definite article, so the word the, potentially followed by some adjectives. So I ran over to the dog. I sat next to the very fluffy cat as an examples. And so here, I ran over to the dog being an example of a noun phrase, and it's a definite noun phrase. The very fluffy cat is an example of a definite noun phrase because it refers to the very fluffy cat, not just a very fluffy cat. And if you remember, I then said that why should you care about that? It's because named entities are found in definite noun phrases. So those are the things we need to look for if we're going to be trying to root out these named entity things. But we also identified that there were some potential problems with this because we don't tend to just refer to nouns by themselves. We've got things like adjectives. We don't tend to say just the cat. It might be the fluffy cat. And we need to pick up both of those types of things. And we need to identify the head noun in a noun phrase. And sometimes there's more than one contender. So the vicar, Brian, or my cat, Bob, you have two potential contenders for what the head noun is there. Is it vicar? Or is it Brian? Is it cat? Or is it Bob? And depending on the semantics of that sentence, that may vary. And so it's not quite as straightforward as it may first appear to look for these things. We talked a bit about parts of speech tagging or pos tagging as well. So remember, parts of speech are the 9 things that we are taught at school and then immediately forget, which are things like nouns, pronouns, verbs, adjectives, adverbs, determiners, prepositions, conjunctions, and interjections. And all words in the English language will fall into one of those parts of speech, and depending on the context, they may be used in multiple ways. So you can have things that are nouns in one context, but maybe a verb or an adverb in another, for example, even an interjection. But all words in the English language will fall into one of those categories. And the labeling of words according to their POS category is known as POS tagging in natural language processing. So if you hear POS tagging, it just basically means that you've gone through some text and you've identified that each of the words belongs to one of these 9 parts of speech if you're doing it in English. Now, parsing is another important concept in natural language processing, and that refers to the process of breaking down a sentence into its component parts and describing the syntactic roles of each component. So things like pos tagging is an example of parsing, or looking for noun phrases is an example of something you would do in parsing. So that, again, you'll hear parsing talked about a lot, and that's basically what it means. It's the process of breaking down your sentence to describe the syntactic roles through various methods like pos tagging, etc. We also talked a bit about regular expressions, which are ways in which we can set up sequences of characters to define a search pattern that's used by search engines, and that potentially we could use that maybe to find definite noun phrases. The issue with that, though, as we discussed, is, because this is the way it used to be done, it's a huge pain. There are vast numbers of potential combinations of pos tags that could form definite noun phrases, and you have to be really careful, because sometimes you'll write a rule that says look for this combination of pos tags, and it'll pick up noun phrases, definite noun phrases, but it'll also pick up things that aren't definite noun phrases as well. So it's an absolute nightmare trying to do it that way. And we also discussed how in a lot of examples of the things we'd want to use it for, where we're looking at free text that may well have been quite hastily written, the regular expressions are less useful because they necessarily assume that the text is written in good grammar, because we're looking for text that follows grammatical rules, or at the very least is consistently bad, and it uses bad grammar consistently. And again, neither of those things are likely to be realistic for the kind of text that we would be looking at. So we then said, well, how can we do this if this using regular expressions approach isn't ideal, it's too difficult. And the beauty of named entity recognition, modern named entity recognition, is we can use this wonderful Python library called SpaCy, which is now probably the foremost natural language processing toolkit that's used in the world for natural language processing. It's used for lots of different things, and it basically uses AI-based methods underneath. So hopefully you've all installed SpaCy, because you're going to be using it today. If you haven't, you can quickly install it with pip install SpaCy when we start the exercise. but it's really, really easy to use. And the way it works is it uses something called a convolutional neural network. Now, we've talked about neural networks now quite a bit in some of the other sessions, but just as a reminder, they're essentially trying to emulate the way in which the structure of the brain works. So neurons connected by synaptic connections, synapses with signals being sent along those connections to the neurons. And essentially neural networks have multiple layers of these nodes which emulate our neurons, and connections between those nodes on different layers. And each connection has a signal that's being sent along it and a weight associated with it. And essentially what you're having is each node will then take, it'll add up the weighted sum of everything that's coming in. So it'll say the weight of this connection multiplied by the value that's being sent along it, added to the weight of this connection, multiplied by the signals coming along it, etc., add them all up, and then shut that number out the other side, which will then usually feed into another layer where this does the same. And we have different types of activation. And basically, these things are quite magical, because it turns out that by using this kind of stuff, these kind of neural network structures, we're able to identify underlying patterns that we would struggle as humans to see, but which the machines can tease out and identify in order that we can train them to predict things given a set of inputs, and where we would struggle to express what it is about the particular rules. A neural network can somehow unpick this, and they're a very black box, because we don't really understand what it means that when the weights have been configured in a certain way. We don't really understand what that means, and that's the great irony of neural networks. They were set up to try and better understand how the brain works, and they're just as mysterious and magical, but at the same time they also work really well as well. So it's one of these black box approaches where we don't really understand why this works, but we know it works, and they're proven to work time and time again. And of course, this is really useful for what we're trying to do, because essentially we've got a problem where we're trying to find these named entities in definite noun phrases, and we know that it's very difficult to try and work out, to list down essentially all of the rules to say this is where you find definite noun phrases in combinations of this, 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 and this, and this. Really difficult to do that. So instead, why don't we train a neural network to try and work if it can work out where they are? And it turns out, as SpaCy uses this, turns out it's really good at being able to work out where named entities should be. And essentially what SpaCy's doing underneath is it's predicting whether a particular word or set of words is a named entity. And it does that based on the words that it's seeing, but also the words before that word and the words after that word at various different distances, and using that information to say, I think I've learned when I see this kind of pattern that it's usually a named entity. And that's basically what it's doing. So we've trained a machine to try and look for these patterns, which are very hard for us to describe, to try and work out where these named entities are. And it's very, very good at being able to do this. So let's see how it works. So hopefully you've all installed SpaCy, and hopefully you've all downloaded this as well, which is the one of the language models. So there are various pre-trained models, SpaCy models, that's basically been pre-trained on huge amounts of text. So large corpuses of text that it's had lots of training on to try and identify things like named entities. And there are various different models available. The NCoreWeb SM is the one we'll be using. The N stands for English. Core Web is basically one of the core models that's been trained on web-based materials. And SM stands for small. There's also MD for a medium-sized set. And there's an LG, I think it is, for the large. The medium-sized set is a gigabyte. I can't remember how large the large one is, but it's pretty big. So for training, we're just going to use the small one, but you may well find if you're doing this in reality, you may want to try it with one of the other pre-trained models as well. And there's also other pre-trained models, obviously for different languages, etc. as well, but also for other applications. So there's stuff that's been trained on medical data, for example, or Twitter tweets. So picking the right pre-trained model to start with is really important. And it's really important in particular because it allows us to make use of something known as transfer learning. And transfer learning is basically where, rather than trying to train everything from scratch, so rather than me having some free text data and then trying to train up from scratch my model on how to pick out all of the named entities, that means if I was doing that, I'd have to train it on all of the kind of stuff that it's going to see in all text. So it's far better to use a pre-trained model that's seen all the common kind of words. It's seen the more sort of general stuff that it's going to expect to see in a lot of things or in everything. And then we use that as the starting point, and then we build up from there. And that's in its transfer learning. So then we start showing it some more specific examples that are more relevant to the particular domain that we're looking at. And then we get it to improve its training from there. So you get it to be very good at sort of general text right out of the box. And then we improve the training by showing it examples and training it on new examples from our own problem. And then it gets better at picking up stuff that's more unique to us. But it means we don't have to worry about training everything from scratch all the time. And it's a really widely used tactic, and is why SpaCy has these big pre-trained models available, so you can get something running straight out of the box. And as you'll see in a moment, you can actually get some pretty good results just from the pre-trained model. So it's a nice, easy, quick way to get some decent results out with a few lines of code. So you're being provided with a file called trumparticle.txt. This is basically just an article from the New York Times about one of Trump's many firings of people, and it's just been copied into a text document. So nothing fancy, it's just a piece of text. And what we're going to do is we're going to use SpaCy to extract the named entities and also what predicted classifications, so are they people, are they organizations, places, etc., from this news story. So I've pre-opened, so you can either follow along with this or you can do that in a moment when we stop for the exercise. But just to show you, so this is the article text, which I posted on Slack and on the GitHub repository. So this is the article that we're trying to grab some named entities from, and just by glancing through it, we can see that there's a lot of named entities, lots of people here, organizations. It's ripe for some named entity recognition. So that's what we want to do. We're going to take our free text and then basically try and automatically extract all of the people, all of the organizations, all the places, etc. So we're also going to open you should have also had a file called Trump extract.py, and this is basically the code that is going to extract the named entities from this text. And as long as this, make sure these two are in the same directory. So if I go into this, I will talk you through this code. Now, you'll probably see, first of all, it's not particularly long. There's not a lot here. In fact, most of this is comment. So hopefully you'll get an immediate indication that actually this may look a little easier than perhaps you're anticipating. It's actually really easy to, if you just want to get some quick stuff out of SpaCy just based on a pre-trained model, you can do that really, really easily. So the first thing I'm going to do in this code, as you're very well used to doing now, is to import the things we need. And basically there's two things I'm going to need for this. I'm going to need to import SpaCy itself, and obviously that will only work if we pip installed it. And I'm going to import this model, the pre-trained English small web-based model that we downloaded earlier as well. And if you use the command that I showed you earlier, that will basically download it into SpaCy. So wherever you import SpaCy, you can import that, and that will automatically pick that up. So once we've done our imports, what we then do is we load this pre-trained model that we've downloaded as what's known as a language. And so we have two key things in SpaCy. We have things known as a language, and basically the language is the trained model. It's the trained model that we're going to be using to be able to do all the fancy stuff like named entity recognition, POS tagging, all that kind of stuff. Because this is the stuff that's been pre-trained. So that's a language, and the other thing is an article. And an article is basically when we've applied that language to a piece of text, the results are essentially stored as what's known as an article. And the article, then we can interrogate the article and ask, what are the named entities that you found? What are the POS tags for this text, etc. So the language is the model that's been trained, and then we apply the language to our free text, whatever it is, and then the results are essentially stored in something known as an article. It's also common convention when we load the whatever model we're using to load it into a variable called NLP, and that's the standard name that we tend to use for our language within SpaCy. You can call it anything you like, but NLP is the standard that's used. So all we're doing here is basically saying load. We've imported this pre-trained model, so load it and then store it in this variable called NLP, and NLP will now be the language that we will use to do its magic. So load this into NLP. Then I'm going to read my file, the Trump article, this one here. I'm going to read that in. And you've seen this stuff before. The only bit that's a little bit different, you have to add in the fact it's UTF-8 encoded. Most standard text files that you'll be using will be exactly that, so you can just get used to putting that in as your second parameter. Be a little bit different if you're using web-based stuff, but don't worry about that for a minute. So we're opening the file, and all I'm going to do, I'm just going to read the entire file in. We don't need to, when we've read in files before, it's typically for modeling, been for grabbing out some parameter values and stuff. But here, we just need to read the whole thing in because it's the text itself that we're interested in. So I can use this .read method of the file. So I can say f.read. And I can call a secondary method on this called strip. And that's a really handy thing because what it basically does is say read the whole file, read it all in as a single string, but to strip out any spaces at the start and end of the file. So just give me the bit I need. And that f.read.strip will then be stored in raw reads. Then we'll have a single string that will store all of that together. So we'll have basically the entire article in a single string. Then what we'll do, now we've got it read in, we've got our language ready and loaded, ready to go, we're going to apply the language to this article that we've read in, and then store that. That becomes, in SpaCy terms, the article. That's the results of the natural language processing applied to it. So all we do is we say NLP, that's what we've called our language, and then we open brackets and we pass in the thing we want the language to apply to. And here it's, I've just called it raw read. That was the name of the string that I read in. So I'm just going to pass it that. And then that's stored in article, this variable called article. And again, that's pretty standard that they tend to use the variable article to indicate that it's the SpaCy use of the word article, which is your sort of where you've applied the language to your text. So we've loaded the language, we've then read in the file as a string, and then we've applied the language to the string that we've read in, and now we've got an article. That has done it. That is your named entity recognition in terms of being straight out of the box. Literally as simple as that. In fact, most of that was just reading in the file, which you've seen before anyway. Now we've got that, all we need to do is then grab out the information that we want. So here I'm just going to take a separate list of labels so that I've got the categories that are predicted to associate with each of its predicted named entities. So SpaCy is basically going to predict, I think this is a named entity, and I think it's of this type. And the type, like person, organization, etc., in SpaCy terms is known as the label. So you have named entities and you have labels. And the label is basically the category of named entity. In SpaCy, the labels are stored alongside the entities, and the labels we can grab using a simple list comprehension here. So the named entities are stored in .ents of the article. Remember, article is the results from applying the language to the text. If we call article.ents, then that's basically where the named entities are stored. And each named entity is stored as an object, and we can grab the .label underscore, make sure you note the trailing underscore here. That will grab the label for each named entity. So as you're used to seeing in list comprehensions now, this is basically saying for each of the objects in article.ent, so in other words, for each of the named entity objects that you found, give me its label. And that will basically return the type of named entity, and that will store it all in a list called labels. So then we'll have a list of the named entities, the named entity labels. And then all I'm going to do, I'm just going to print them. So I'm going to print each named entity alongside its label. So I can just go through a simple for loop across the range of the length of article.ents, which is will be a list of objects, with each object being the named entity that it's predicted, and give me the entity itself. So that's article.ents, whatever index we are in the for loop, and then I'll put a little colon, and then the corresponding label for that. So let's run it. Let's see what happens. So remember, this is the article, the news article, I should say. And this is hopefully going to pull out some named entities. So let's run that. There we go. It's done. Now, if we scroll up here, you can see what it's done is it's done exactly what we hoped. It's pulled out a list of named entities alongside the label, the type of entity that it is, or that it predicts it to be. And scrolling through, we can see it's done a pretty damn good job. It's picked out Washington as being a named entity, which it is, as a name of a place, and it predicts that's a geopolitical entity, which it is. Peter Strzok as a person, correct. FBI is an organization, correct. Trump as a person, possibly debatable, but we'll let it pass. Hillary Clinton, person, Russia, GP, etc., etc. It seems to have done a pretty good job here at pulling out, and all we've done is just use the pre-trained model. So this model won't have seen this particular, or it's unlikely to have seen this particular article. This has just been pre-trained on a huge corpus of text. And again, this is just the smallest data set that it's trained on. And it's done a pretty good job, straight off. That it's actually managed to pull out lots of named entities. And it's seems to have predicted pretty well what the entities are. And it's as easy as that. Essentially, those 3 lines of code, plus your imports, will do it for you. That's it. That's how easy SpaCy is to use if you're just using the pre-trained model out of the box. Now, for your projects, you're probably going to want to be doing some additional training, which I'll show you how to do this afternoon. But certainly as a first step, this is what you would do. You would run it with one of the pre-trained models. In fact, you'd probably run it with multiple pre-trained models and compare the named entities that it's predicting with the named entities that are in there and see how well it's doing. Before we move on, any questions about that so far?
Just a general question. So this is natural language processing seems to be based around recognizing named entities. Are there any techniques that use other parts of speech instead?
So it's not, obviously it's not all named entities, and we look at tone on Thursday when we talk about sentiment analysis as well. But do you have any examples? I'm struggling to think of.
So that would sort of pull out verbs, for example, yeah. So I guess that would then feed into the tone of the article,
yeah. So you can. So if you wanted to pull out, for example, verbs. So SpaCy's. I mean, we don't show this in this course, but SpaCy's got that built in too. So when it does this NLP, when it applies the language and to this text, and this is basically where the magic's happening, and then feeds that out to the article. It's not just done named entity recognition. That's one thing that we've tapped into. It's also done pos tagging. So it's automatically predicted what each of the words within it are, what their pos tag is. So are they verbs, are they nouns, etc. So you can really easily pull out. So if you're just looking for all the verbs, you could pull that out. If you're looking at verbs that met a certain condition, you could pull that out. You could look at verbs that were close to a named entity, for example, and combine the things. So yes, you can absolutely do that. It does loads of stuff, and there's lots of materials that I can show you, point you to that talk about all the extra stuff that it does. It's got some really nice features that allow you to do sort of word trees and stuff like that, where you can it's try to judge the semantics of the sentence and what the pos tags are. So yeah, there's lots more to it than than the named entity stuff. But the key thing with the named entity recognition is very often when you've got a body of text, and you're looking to extract information from it, you're very often wanting to pull out the things that are being talked about. So that might be people, it might be certain medications that they've been taking, it might be their conditions. You could train it to pick up medical conditions, or particular places, hospitals, for example. Those are the key things that you want to usually automatically extract for this kind of purpose.
Right. Great. Thank you.
Yeah, no worries. Any other questions? Okay, so in which case we'll go into the first exercise. But before we do that, so there is a bit more to SpaCy than this, as I say, and I'm going to show you in the second half of this afternoon how you add to the training. Because that's where it gets really good, because it might be very good at picking out an article on Donald Trump, but we then need to know how good is it if we apply it to our patient notes. The answer is it'll probably be pretty good, but there's probably lots of things it'll either miss or misclassify, and so that indicates we need to add to that general training to say, this is the kind of thing you haven't seen much of before, so I'm going to need to train you on the kind of text you're going to see in my domain, and allow it to try and pick up on the how to best extract these named entities on your text. And I'll show you how to do that. So before I go into the exercise, in order to make this exercise a bit easier, there's a few extra little Python things that you may want to make special note of that we haven't taught you how to do yet, but are very handy little extras, particularly for this exercise. So these are useful things to know in Python generally, and you may well find other applications for them, but they're particularly useful when you come to do this exercise and for natural language processing. So the first one is the count function. The count function is something we haven't actually shown you, but is actually really useful. You can basically call the count function on any iterable object, such as a list or a dictionary, and it will basically just count how many items match whatever value you give to it. So if we've got here a list, I've called list A, with these values 1, 2, 3, 3, 2, 2, I can then use count and pass in the number 2 and say, and that will count how many 2s are in that list. Okay, and if I run that, it correctly prints there are three number 2s. So that's it's quite a simple little function, but you will find it quite useful for things such as this. Now, we've also shown you already, and you've had lots of practice of using list comprehensions. There's actually something else in Python that's very similar, known as a dictionary comprehension. And as you would imagine, this allows us to do the same as for lists, where we do that sort of shorthand single line of code that essentially replaces a for loop with a single line to generate a new list. It's just the same here, but this does it for dictionaries. And it works in a similar manner to how you might expect. So let's imagine we've got our list here again, list A. We've got our 6 numbers. And let's say I want to create a dictionary that lists for each key value, it lists the number, and then the value represents how many times that number comes up. So essentially, I want a dictionary that says the number 1 as the key, and then says that comes up once, the number 2 as the key, and then the value is 3 to say that came up 3 times, and then a key of 3 with the value of 2 to indicate that came up twice. And that can be quite useful. And I can do that really easily using a dictionary comprehension. So in the same way, we give it the name of the dictionary, the new dictionary that we want to create. So I've just called it frequency dictionary. And then, as you might have guessed, because dictionaries use curly brackets, we use curly brackets rather than square brackets to indicate that this is a dictionary comprehension. And this shouldn't look too bewildering to you if you're used to list comprehensions. Let's just break that down for a minute. So what is usually easier with a list comprehension or a dictionary comprehension to start in the second bit. What this is basically saying, for each number in list A, so for each of these, then give me the number, so the value itself, colon, because remember in a dictionary we have key, colon, value. So give me the number itself, a colon, and then give me the frequency, which I've just shown you. You can use count to do that. So give me the count on list A for that number. So basically what that will do is it'll create a dictionary that looks at each number in list A, and each entry will be, the key will be the number itself, and the value will be the count of how many times that number comes up in the list. And obviously this could be anything, this is just an example. But that's how you create a dictionary comprehension. And if I print that, you can see that's exactly what it's done. It's printed, the value 1 comes up once, value 2 has come up 3 times, and the value 3 has come up twice. So that's a dictionary comprehension. And the third thing I want to show you is something called a collections counter. So there's a library called Collections that has lots of useful stuff in it. One of those useful things is a module called counter. So if we write this import statement from collections, import counter, so from the collections library, import the counter module, this gives us access to some really useful methods to count things in lists, and includes things like we can easily grab the 10 most common values in a list, for example, the 4 least common, and things like that, just using very simple methods. So it's a really handy little module. So let's imagine we wanted to do it to count the X most common values. So imagine we've got our list here again, same list as before. I can use the counter module and the most common method of the counter module to count, for example, the 2 most common values within that list. So here, what I do is I say counter, note the capitalization. I pass into that the list I want it to count, that it wants to apply the count onto. So in this case, it's list A, and then use the dot, and then I call the most common method of this to say, count these items, do your magic counter, and then give me the most common, and the value we pass in here is just the X most common. So if I wanted the 10 most common, I'd pass in the value 10, and that will give you the 10 most common, etc. So then I store that in this variable here and print it, and you'll see what it returns is this list of tuples. And remember, a tuple is a ordered set of values that can't be changed, as immutable. And so here we've got 2 tuples because I've asked for the 2 most common. So each tuple is basically, the first element of the tuple is the value, and the second element is the frequency. So when we call the most common method, it will return this as a list of tuples where the first value in each tuple is the value itself, and the second value is its frequency. So if I call that on its list, we can see just by glancing at it, the most common value is 2, because because there's 3 of them. And the second most column value is number 3 because there's 2 of those. And so that's what it's returned. It's returned the value 2, which has frequency 3, and the value 3, which has frequency 2. They're the 2 most common elements, the values 2 and 3, and these are the frequencies of those 2 most common elements. So these 3 things you will probably find quite useful in your general Python programming, but you will particularly find useful for this next exercise. So that's a big hint there. You may want to use these things in just a moment. So the count function to count how many items in something like a list or any other iterable object match a certain value. A dictionary comprehension, which works just like a list comprehension but sets up a new dictionary. And the collections counter, which allows us to do handy things like grab the X most common values. So I want you to, I'm going to split you up into groups, and I want you to, for the first exercise, extend this code in trumpextract.py. Now, I'd recommend you take a copy of it first. You've still got the original in case anything goes wrong. And I want you to extend the code to do the following. I want you to store the named entities and their frequencies that SpaCy has picked up within the article in a dictionary with the keys representing the named entity strings, so the named entities themselves, so trump, etc., and the values in that dictionary representing their frequencies. So if trump comes up, I don't know, 17 times, then you should have an entry that says trump as the key and 17 as the value. To do that, you should first grab the named entities that SpaCy has pulled out, convert them into strings because they will not be stored as strings, they're stored as objects and they're stored as tuples within those objects. You need to grab them out as strings, and remember your experience of casting into different types of variables for this, and store them in a list. So grab the named entities, convert them into strings, store them in a list, then use a dictionary comprehension, which we've just learned about 3 minutes ago, to create the dictionary as described above, with each named entity text as the value as the key, and then the value representing its frequency. Once you've done that, I then want you to print the 10 most common named entities in the text. I also want you to print the 16th sentence of the article. Remember, we start counting from 0. Begin there. And the sentences of an article, of a SpaCy article, are stored in article sense, article.sense, not to be confused with article.ents. So article.ents is where your named entities are stored. Article.sense stores the sentences of your text. Then I want you to create a set which contains only unique named entity labels. So your types of named entities. So you should have a list of things like org, person, GP, etc., but unique names. So we only want each of those to come up once at most. Now remember, back from your early Python training, that a Python set only contains unique values. So if you cast something as a set, it'll automatically remove the duplicates for you. So if you had a list that had the values 1, 2, 3, 2, for example, and you cast that list as a set, it'll automatically remove the other 2, and it'll just return 1, 2, 3 as a set. So that's a very big hint on how you will do this bit. And then lastly, I want you to print the set of unique labels to the user, and then ask the user to select one of the labels. So let's say the SpaCy is found in this article. There are organizations, there are type person, there's type GPE, and want your code to say, here are the named entity types that we found, and then ask the user to select one of them. So then if the user types, for example, org, then I want you to display to the user all of the named entities with the label org. So whatever they type in, whatever label they select, that should be the type of named entity that's then printed out. And your hint for this is to use a list comprehension to grab the named entities from article.ents. That's where your named entities are stored. Remember to cast them as strings. where their corresponding label meets the condition you need. So use a list comprehension. You can do this in a single line of code. You want to grab the named entities from article.ents, albeit cast out as strings, where the label for that named entity meets whatever condition you need. And in this case, that's defined by the user. Then all you need to do is just cast that list as a set to remove any duplicates. And for extra points, though don't worry if you don't get this far, you can put all that in an infinite loop so that the user keeps selecting labels and prints a warning message if they type in a label isn't recognized. But don't worry about that if you're struggling with the rest of it. The key things to do are the main bits in 1 to 5. So I'm going to give you about 40 minutes to do this. We'll resume about 3 o'clock. I'm going to put you into breakout rooms and have a go at this. So this is testing how you're going to, now SpaCy's done its magic, how you're then going to get that information out. And this is all using stuff that either you've seen before or you've seen back here. Okay, any questions about that? Okay, in which case I will stop sharing. Oh, no. Pause. Okay, and I'll share my screen. So this is the solution. So everything's bolted on to the end of the code that that I gave you. So the first thing I asked you to do is print all of the named entities with their frequencies, and I suggested the best way to do that would be to first of all grab it as a list, and then you could use a dictionary comprehension to put that into a dictionary. So you've got the entity against their frequency. So here I use a list comprehension, and basically what I'm saying is for each named entity in article.ents, cast that as a string, because it needs to be cast back as a string, and that will give me a list of strings representing the named entities in article.ents. And then now I've got it in a list, I can then create my dictionary using a dictionary comprehension. So I've just called mine any frequency dictionary. And just as we did for the example, I'm saying here, for each named entity in that named entity list that I've just created, I want to set up the dictionary such that the key is the named entity, so whatever the text of the named entity is, and the value is the count, i.e. the frequency. So count how many times that value appears in that list. And that will automatically bring up a dictionary where you have the named entity as the key, and then how frequently it occurs as the value. Then I asked you to print the 10 most common recognized entities with their frequencies. Again, I gave you the hint of using the counter from collections to do that. And so now we've got it stored in this nice list up here. You can either do it on the list or on the dictionary. It doesn't matter which one you do. It'll work on both. Counter works on any iterable object, including dictionaries. So you can just apply this straight to the dictionary if you want, which is what I've done here. I called counter. Now, a question came up, which I don't think I explained. You're probably wondering why there's a capital here, and it looks like you're calling a method. In fact, that's not what you're doing. What you've imported is the counter class from collections. And what you're doing here, the method that's being called is the most common method of the counter class. And this iterable object that you're passing in this case, the dictionary, is the input that class needs. So just as when you create a class, and sometimes you need, so when we looked at before for SpaCy, for example, we looked at you pass in a patient ID when you create a new patient. Here, when you create a new counter, we're passing in the thing that it's going to be doing the counting on. So that in the constructor underneath, that's what it's assigning. So we pass in the thing we want to count, or thing we want to count on, the iterable object, and then we call the most common method on that and pass in the number of most common we want. So in this case, 10. And that will then return the 10 most common named entities. 16th sentence to print, which will of course be sentence number 15 in the article, because we're starting counting from 0. So I probably should have given a bit more of a hint, and hopefully you got the message that I broadcast about this. So the easiest way to do this, a number of you picked up and tried to do it, is article.sense and then square brackets 15, which is almost there. It's unfortunately stored as a generator. So all you need to do is convert it into a list, and you can do that using simple casting. So we can say, make that a list, and then I can treat it as a list. So if I cast cast article.sense as a list, and I'll call that sentences, I can now work with that as though as a list, and then I can just call sentence index 15, which will be the 16th sentence, and that'll print the 16th sentence. Then I want to list the unique named entity categories, i.e. the labels, that are predicted in the text, and ask the user to select one to see all the named entities predicted in that category. So the first thing I'm going to do, I want a unique list of all the labels. Now, we already grabbed the labels up here on line 30, because we basically grabbed the label for each of the named entities through a list comprehension. We stored it in a list called labels. So if I cast that list called labels as a set, that'll automatically remove any duplicates, and it'll just then leave me with a unique list of, unique set of labels. So however many named entity types that it predicts, those will be the labels, and they'll be stored in here. Then what we need to do is basically print those out to the user, tell them to select one of those, and then get Python to print out all of the named entities that SpaCy predicted that have that category. And this was a little bthat more difficult, this final bit. So I put it in an infinite while loop. You don't have to do this, but basically it says keep doing it so that the user can keep selecting. I print out a message saying I found the following named entity categories. I print out each label in that unique label set. So if it's found 5 different types of labels, it'll print those 5 different types of labels there. And then in here, again, you don't have to put this in an infinite loop, but I have, so that if the user selects a label that doesn't exist, it'll ask them to input it again. But basically what you're wanting to do is get the input from the user. So in my code, it just then checks to see if it's in this unique label set. But again, that's just a fancy extra. You don't need to do that. And then based on what the user's input, we then need to basically find all of the named entities that SpaCy found that it predicts are of that type, that have that label. So I'm doing it through a list comprehension here, which looks a little bit confusing at first, but let's just break this down and think about it. Again, we'll start not with the first element, but with the 4-bit, because it makes it easier to understand. So what this is saying is, for each named entity in article.ents, which is where our named entities are stored, if the label for that named entity, remember the label is stored as under .label underscore for that named entity, that stores the label for that named entity. So if I cast that label as a string, and that equals whatever the user input, then that's the condition that needs to be met. And then I want you to give me the named entity cast as a string. So for each named entity in the list of named entities, if the label for that named entity is whatever the user input, then give me back the named entity cast as a string. So what you'll end up with here is a list of named entities cast as strings, but only where their label is whatever the user input. So if they input person, it'll only give me a list of named entities cast as strings where when we checked against the label, it was label person. So it'll only give me back people, hopefully. And then I can then just convert that, because what that'll do is it'll include duplicates. So if Trump is mentioned 11 times, I think he is, then it'll include 11 instances of Trump. So again, we can just convert this to now we've got this list, we can just convert that to a set. So we've only got unique values. And then I can just print that out. So if we show that running, so you can see here, first thing it did was the dictionary. So it's set up the dictionary with each named entity along with its frequency. and then it's printed out the 10 most common named entities, which struck FBI, Trump, Russia, Clinton, etc. And then the 16th sentence, this decision should be deeply troubling to all Americans. And then it found the following named entity categories, which is naught, person, org, ordinal, GPE, cardinal, and date. It's possible yours might be different. Remember, it is an AI, so it might vary slightly, but it should be largely stable. And then it'll ask me which type do I want to see. So let's say I type person. If I type person in here, it'll then list all of the named entities that SpaCy found that it predicted had a label of person. And it seems to have done pretty well. They all look like people to me. Trump is debatable, but as I say, but if I then try that again, let's try date. And it's picked out all the date. Remember, date is a weird kind of named entity that is counted as a named entity. So 60 days, 20 years, June, these are all date type entities. So it seems to be doing pretty well. Any questions about any of that? Good. Okay. So hopefully you've seen so far that actually using SpaCy straight out of the box is actually quite straightforward. And you can get some pretty decent results, at least on an article about Donald Trump. Anyway, we seem to be getting some pretty good results straight out of the box. But in reality, when you start to use this in earnest, as a number of you will be doing for your projects, you will find that it's good, and and you should always start with the pre-trained model and see how good it is. But you'll find that it won't recognize everything. There are bound to be things, particularly in your particular areas, whether it's policing or health, that it's going to come across named entities that it won't pick out because it hasn't recognized that kind of writing, or it hasn't recognized those kind of entities. There'll basically be words and syntactic patterns that it just hasn't seen before, and it hasn't been able to generalize to. So there are two key things that you can do. The first is you can select a better pre-trained model. And as I say, there are different types of pre-trained model. In fact, there's lots that you can choose from. We're using the small English web-trained model, but there are different sizes of that one. And there's also ones that have been trained on things like blogs or news stories or comments on social media, for example. By picking one that's been trained in a particular special area, you may find that's a more sort of natural fit for what you're trying to do. You might find you get better accuracy right out of the box. But even so, you're probably still going to want to update the training to improve it for your particular examples. And so we can do this using SpaCy. We can basically open up SpaCy, open up the pre-trained model, shove some new examples in, and then get it to run its training again on these new examples. So it adds to the training it's already got. It doesn't replace the model we're already using. It adds to that pre-trained model. So it goes back to the transfer learning that we talked about. So you'll see I've also given you a file called Trump article enhance.txt. And if I open that up here, so this is exactly the same article as you saw before, exactly the same article text, with one key difference. If I can find it. There we go. So it now reads, President Trump in inflammatory text messages and helped oversee the Hillary Clinton email and Russia investigations, as well as being a famous member of Pencord. Now that, unsurprisingly, wasn't in the original news article. I've added in this little bit here. Now, if I were to run this using the conventional, in fact, let me do it so you can see. So if I go back to this one, so all I'm going to do, I'm just going to, this is the exercise code we just looked at. I'm just going to get it to look at this enhanced article instead. So I run that. And my kernel has died. What's happened? This seems to be a growing theme today. Let me restart. Sorry, this doesn't like something. Here we go. Right. Still doesn't like it. Okay, let me close down Spider. Worryingly, my computer sounds like it's about to take off. I'm not quite sure what it's processing. But, let's open Spider back up. Let's try running it. Ah. Where is it? Let me find the file. Sorry. Right, let's try it again. Here we go, right. So it's done the same as before, except this time it's looked at this new article that's got a mention of Pencord, and sure enough, it picks out Pencord as being a named entity. Now, I would hope it would pick it up as an organisation, because that's kind of what we are. If I type in org, though, it's not listed. So let's see what it is. Is it a person? No, hasn't picked it up as a person. Is it a NORP? No. Is it a GPE? Yes. So SpaCy, out of the box, thinks that we in Pencord are a geopolitical entity. Now, we may have delusions of grandeur, but I don't think even we can claim that we are a geopolitical entity in the same vein as something like the United States or Russia or China. And so it's got that wrong. So it's picked out, it's great that it's found Pencord as a named entity. Remember, it has not seen the word Pencord. So it's great that it's identified and predicted that's a named entity. That's brilliant. But if we need it to also pick out what type it is, then it's got that wrong. It really should be an organisation. So let's see if we can improve matters here. So if we have a look at, yeah, okay, sorry about that. So let's have a look. I've put in another file as well called Trump. Let me just change this back so I forget. So I've got another .py file called Trump extract add to training. Sorry, one, yeah. So what I'm going to show you here is, can we train SpaCy to recognize Pencord is an organization? Okay. So what I'm going to do, I'm going to start off my code in a similar way by importing SpaCy and importing ncore WebSM as we did before. There's a few extra things that I'm going to import here too. The first is I'm going to import some utilities from SpaCy, from spacy.util. I'm going to import something called mini-batch, and I'm going to import something called compounding. Don't worry too much about this at the moment. I'll come back to those in a second. And I'm also going to import the random library, which you're well used to using. I'm going to use that to shuffle around our training data. And again, I'll come back a bit to that in a moment. So if I were to run this first block of code, in fact, I could have done it here. If I, let's just see this again. So if I just do this first block of code here and run that, you can see, so it's listed out all of the named entities and their types. And you can see, sure enough, Pencord has been listed as a geopolitical entity, which is wrong. It's great that it's picked it up, though. That shows how powerful SpaCy is, actually. So let's see if we can improve this. What we need to do is we need to give it some examples, some new examples, to help it recognize that Pencord is an organization, not a geopolitical entity. The way we do that is we basically open up what's known as the SpaCy training pipeline, which is just basically a fancy way of saying open up, pop open the car bonnet, basically. We're going to start tinkering around underneath. So SpaCy's very user-friendly in terms of it doesn't make you worry too much about all of this, but if we want to add to the training, we're going to need to get down underneath the bonnet and tinker around. So the first thing we need to do is, so basically the training SpaCy is made up of a number of training pipeline components. Don't worry too much about what that means, but essentially there are different pipelines that are used for different bits of what SpaCy does. So as I said, SpaCy doesn't just do named entity recognition, there's also pos tagging and all sorts that it does. What we want, we're only interested in the named entity recognition bit. That's the bit that we need to add to the training. We're not trying to train it on pos tagging better, for example. So the way we do that is we need to grab that pipeline, the named entity recognition pipeline, which is known as NER in SpaCy. That's it's got a label of NER. And we can use this get pipe method of the language, which remember we stored as NLP. So this is on the NCore WebSM model. This is the pre-trained model that we're opening up, okay? So what this does is it says to open up basically the named entity recognition bit, because this is the bit we're going to need to chuck in some extra examples, get it to learn it, and then close the bonnet. We store this, we use get pipe to get the named entity recognition stuff, and I'm going to store that in this variable I've just called NER pipeline components. Now, what we're going to need to do is we're going to need to give it some example sentences that will help it identify that Pencord is an organization. Now, obviously, if you were doing this in reality, there'll be much more than just trying to get one thing recognized. You're probably going to, you essentially have maybe hundreds, maybe thousands of examples that you're going to give it for your particular data. But here, we're just going to use a simple example so you can see how this works. And all I'm trying to do is basically get it to recognize Pencord correctly. So I'm just going to give it a couple of example sentences. So I've just got a list of 2 sentences here. The first sentence is Pencord is a fantastic team because Dan Chalker's in it, and Mike Allen loves system dynamics. Now, both of these sentences would probably fail at any sarcasm detection, but nonetheless, they are useful sentences for training our model. And they're useful because we're also going to try and train it at the same time that not only Pencord is an organization, but I'm going to try and train it to recognize system dynamics as a work of art. And again, that may be debatable, especially for anybody that hates system dynamics, including Mike. But nonetheless, that's what I want. I want SpaCy to now recognize Pencord as an organization and system dynamics as a work of art. So I've given it some example sentences here. What I also need to do, though, is I basically need to tell SpaCy within that sentence, this is a named entity and it's of this type, and that's a named entity and it's of that type, okay? So in this first sentence, we've got 2 named entities. We've got Pencord and we've got Dan Chalk. Now, it may be that it already recognizes Dan Chalk as a person. And in fact, it will. I think I've tested this, as it does with Mike, but bizarrely it never used to. You still have to say, you can't just say, well, it already picks up Dan Chalk as a person, because if you don't tell it it's a person, what it'll actually think is, okay, so that you've given me an example, you've said Pencord is a named entity, but you haven't said anything about Dan Chalk. So I'm assuming that Dan Chalk is not a named entity, and therefore I must learn to ignore it. So you need to flag them up, even if they are named entities that it would already pick up, because it needs to know all of the named entities and what types they are. So in this sentence, we've got Pencord, and we want to recognize that as an organization, and Dan Chalk as a person. And then in the second sentence, Mike Allen as a person, and I want to get it to recognize system dynamics as a work of art. Now, I could set up a separate category, as I talked about before, create a new category called modeling methods. And you could do that. The issue when you set up a new category is you need typically thousands of examples to get it to train properly, to understand this type of thing as a modeling thing, or whatever it is that you're newly creating. So where possible, it's always best to try, unless you've got thousands of examples that you can give it for training, to try and fit it in to one of the categories that's already given. So those are my sentences. Now, here begins the fun, because SpaCy is a wonderful thing. Where it falls down slightly is in the way in which you have to have to give it training information, which is basically quite a complex structure. So this is going to be a little bit difficult to get your head around. So I apologize. You will probably need to read back through this as well to make sure you understand how it's working. The advantage, though, is that you always do it in exactly this way. So once you understand what's happening, you can literally, well, I was going to say copy and paste. The best thing to do would be to write a generic function that does this for you. So every time you need it to feed in new examples, you just call this function and it'll do all this organization of the format in which the new examples need to be in for you. Because as you'll see, it's a little bit messy. So what I've done here, and this will make more sense in a moment, is I've set up a list of lists. So, and I'm going to use the colouring here because we're about to enter bracket overload and it's going to get worse. So I've got a list of named entities, and within that list, I've got two separate sublists. Okay, one here, one here. And basically each of those sublists refers to one of these sentences. So I've got two sentences. So the first one relates to sentence 1, second one to sentence 2. The first element of each sublist is the sentence that I want to give it. And in this case, I've stored these sentences in this list of training sentences here. So I've just said it relates to the first one, which is number 0. So it's this sentence. The second element of the list is another list. There's another sublist. And this is a list of lists where each sublist represents a named entity that you want to declare in that sentence. So the first element here is the sentence. And then I'm going to have a list of lists within the list of lists that represent so for this sentence, what are the list of named entities? So the first named entity that I want to declare is pen cord, and I declare that by setting up a list of 4 elements. I give it the text that represents the named entity, so the text pen cord. Then the start and finish characters, I'm just going to leave these at 0 for a minute, and you'll see why. And then the label. So here I'm basically saying, in this first sentence, there's a named entity called pen cord. This is where I'm going to store where it is within that sentence, so SpaCy knows where it is. And it's of type org. And then there's another named entity in this sentence, and that's Dan Chalk. This is where I'll store the start and end characters, so it knows where it is. And this named entity is a person. Okay. So that list of lists here is the list of named entities with these 4 elements in each list for each named entity. Against this list of lists is the second element of this list, which contains the sentence and this list of lists. I bet you're already hating this. Believe me, it's painful, but once you get the hang of this, it's okay. You will get it. There's a reason we have to do it like this. Again, for the second one, so this is the second sublist in the main list. First element is the sentence, and in this case, the second sentence. Then I've got my list of named entities, with the first list being a list of 4 items saying the Mike Allen, the start and end positions, that say they're just 0 at the moment, and then the type of named entity, the label, and then the same system dynamics. So we end up with this multi-bracketed list of lists. The reason we do it in this way will become apparent in a moment. So we've given it some sentences, and then we've set up this list of lists, which will indicate the sentences and the named entities within those sentences. Now what we want to do, we want to say for each sublist in this list of named entities. So that refers to these here. So this is the sublist. There's 2 sublists in that main list, 1 for each sentence. So for each sublist, which is broken as a sentence and then a list of lists of named entity properties, Then for each of the sublists within that sublist, so for each of these named entity blocks, basically that's what it's saying. Then what we want to do, and the reason that says sublist 1 is because it's the second element of this sublist. So we've got the sentence and then the list of named entity stuff. So it's sublist 1 will give us the list of named entity stuff, which in itself is this list. So for each of those, now I'm going to find the start and end characters of each of these sentences. Now we could manually type them in, but that would be pretty painful even for 2 sentences, let alone if you had thousands of them. So we can get, using some inbuilt Python functions, we can tell Python to find the start and end characters of each of these words, each of these strings, I should say, sorry. And we do that using the .find method. And basically what the .find method does, if you call that and give it a string, it will find the starting character index for that string. So if we, well, let's have a look here. So essentially what we're doing is we're saying sublist 0, so remember that's going to be the sentence, is this bit. On that, call the find method. Remember this is a string, so we can call the find method. And then the thing I want you to find is this bit. Sorry, this bit here. So whatever named entity sublist I'm in, I want the first element, element 0, which is the named entity itself. So in the first example, it's saying in this sentence here, which is this one, find that string of text, pencord. And it'll return the starting character, which in this case is actually 0, because it's the first word. So that will give us the starting character for that. To find the end character, we can simply use the len keyword. If you call the len of any string, it will find the length of that string in characters. And so we can just say, give me the length of this word, pencord. And by doing that, I can say, well, the end character then is whatever the start character was, plus how long that word is in characters. Remember, because we're dealing with named entities, they may be multiple words, as in Dan Chalk or Mike Allen. And so it'll count all of the characters, including the space and any other punctuation that might be in there. So that gives us the start character. Then we find the length, we add that to the start character, and that gives us the end character. And that means now we can update these numbers to be the correct start and end characters. So I can set my, remember, any prop list here is whatever list I'm in, sublist for my named entity. So update element 1, which will be the second one, which will be this one, to the start character, and update element 2, which will be the third one, which will be here, to the end character. So then by doing that for all of them, it'll go through, look at each sentence, it'll look at the named entities we've declared, and it'll find the start and end character for each named entity. The last thing we need to do, once it's done that, is to add the label that we've declared, so organization, person, whatever it is, to the named entity recognition pipeline. And we do that using the add label method on the pipeline components. Remember, we grabbed the pipeline components we want up here, where we said we want to grab the NER pipeline. We use a method called add label, and then we give it the label, which is the element number 3, the fourth element of the list. To say we need to give it, we need to add this label into the list. And the reason we do that is because it might be a label that it doesn't already know. So if I'd have written System Dynamics modeling method here, that would ensure that it now knows about things called modeling methods, because not all of these it will necessarily know at the start. So this bit is all about basically trying to get the data in the right format so that we can say, this is a training sentence that has 2 named entities. One of them is here, and that's an organization, and one of them is here, and that's a person. Once we've got that, we now need to start trying to stuff it into SpaCy. Now, in order to do this, because we need to set SpaCy to train, we basically need to switch off all of the other training because we don't want it training on anything else other than the named entity stuff. So basically, we have to turn off all of the other pipelines so that only the named entity recognition stuff is switched on. And the way we do that is we grab all of the other pipelines. And an easy way to do that here is to use a list comprehension where we say here, for every pipe in NLP.pipe name, so give me all of the pipe names, if the pipe name isn't NER. So this will then return a list of all of the pipeline names that SpaCy has that aren't NER, which is the one I do need to leave open. So now we've got a list of all of the ones and we can easily switch those off, okay, which we'll do in a moment. Right, now if you're wondering why we had to do this absolute mess up here, it's because of this. So SpaCy, in order to parse in the sentences and the named entities, you have to parse it as a list of tuples where the first element of each tuple is the sentence, and the second element of each tuple is a dictionary where the key value is the word entities, and the value is a list of named entities stored as tuples. And if you didn't understand that, don't worry, I have to reread that several times, but hopefully this will explain it a little better. So basically, SpaCy has to have it in this format where we have a training sentence, so we've got a list, and then we've got a tuple. Now remember, a tuple are these bracketed things that are like lists, but they're ordered, the order matters, and they're immutable, which means once you set them up, you can't change them. That's why we have to go through all this faff, because once we've got them in, we have to get it right first time, because we can't change it. So they all have to be set up ready. So we declare it as the tuple, dump them into the list, and then give it to SpaCy, which is a bit of a nightmare, to be honest. But like I say, the advantage is you always do it exactly like this, because this is exactly how SpaCy needs it. So for each sentence, we'll basically have in this outer list, we'll have a tuple. So these are the normal brackets, the curved brackets. So the first one, if we take the first training sentence here, the first element in that tuple would be the sentence itself. And then the second element would be a dictionary, as noted by the curly brackets, where the key value is just the word entities, or the string entities, I should say. And then the value against that key is a list, and that list lists all of the named entities as a list of tuples, these brackets, where each tuple, each named entity is essentially represented by the start character, the end character, and the label. So where the named entity is in the sentence, both the start and end characters, and the label that we're giving it, whether it's org, person, whatever it is. And so if you've got two named entities in this sentence, then you're going to have a list of two tuples within this dictionary, which is the second element of this tuple for that sentence, which is in itself in an outer list. Does that make any sense? I realize this is horrible, and you will probably need to read this a few times, but as I say, copy and paste, because this will always work. So basically what we do, this here is all about then stuffing all this prep stuff we've done up here into exactly this format, which we have to get right the first time because it's a tuple, so that we can pass it over to SpaCy. So basically we go through the sublist, each sublist that we had in list of named entities up here, which remember we've updated now to have the correct start and end characters for each named entity. And then I start a little list here for each one, because that's going to be how I assemble the things ready to stuff in. Then for each named entity for this sentence, I'm basically going to add the elements at any prop list 1, 2, and 3. So within sublist 1, so we're in this bit, I need to give it, remember, the start character, the end character, and the label. So this bit doesn't need the text itself. We just needed that here so that we could get the start and end characters. So we need to give it this bit. So grab those bits. Sorry, there we are. Grab those bits and stuff those 3 things into a tuple. Remember, we can't change this once we've done it. So here, which is why we had to do the character finding above. So here I'm assembling a tuple that's got 3 elements: the start character, the end character, and the label type for that particular named entity for that particular sentence. And I'm going to add that tuple to my list of tuples for this sentence, because remember, basically what we're trying to form is this bit where we've got a list of tuples, so a list of named entities for this sentence. So it'll go through all the named entities for that sentence. Once it's got all of the named entities for this sentence, then we can then get it into the correct format, because we need to do an outer tuple that is composed of the first element being the sentence. So that's here, that bit. And then the second element is a dictionary, where the key is the word entities, and the value is our list of tuples, that bit, which we formed up above. So that then gives us the sentence and list of named entities in terms of their start and end characters and labels for one sentence. We can then append that outer tuple to our training data. I set up a new training data list up here. And then we do that for every sentence that we've got. Okay, so for every sentence, you'd go through all of the named entities and stuff them into a tuple, and then stuff that into an outer tuple that is part of a dictionary. So the first element is the sentence, the second element is a dictionary, where that sublist of tuples representing your named entities is the value on that dictionary. I appreciate that. As I say, that's a lot to take in. So you will probably need to read. I've written extensive comments on this to explain how this works, and it is a complete pain in the bottom trying to do this. But unfortunately, you have to do it this way because SpaCy needs it as tuples, and they are immutable. So you have to get them all prepped and then dump them straight in. Is the only way it works. So it's a bit of a pain, but like I say, you can, once you've worked out what's going on, you can copy and paste this code, and this will always work for you. Right, so once we've got it in the format, that's actually the difficult bit. The easy bit is now just training it. So we've got it in the right format now. So what we're going to do is we're going to set up the number of training iterations it wanted to go through. So 100's a pretty good number to start with. Remember when we talk about this is a neural network training, so this is the number of epochs that will go through, the number of full passes through of all the data that's going to stuff through. And then we're going to basically do the training. Now, because we're using SpaCy, we don't have to set up the neural network itself. It's got all this underneath. So SpaCy will do all the hard work for us here. So what we're going to do is we're going to train the model with our new training data that's now nicely formatted in the way we need. The first thing we need to do, remember though, I said we need to turn off the other pipelines. We can only have the named entity recognition one open. But remember, up here, I grabbed the list of all of the pipelines that weren't the one, that isn't the one we need. So in this case, NER. So all of the other pipelines are now stored in this list. So what I can do is I can use a with statement here to say so do all of this with all of this turned off, basically. So by calling the disable pipes method of NLP, this will turn off everything that I pass in here. And in this case, that's the other pipelines list that I stored up here. So basically turn off all the other pipelines. Don't worry too much about the asterisks. That just means unpack everything in that list. So it'll take that list and it'll unpack it sort of into that argument. So it'll just give it the list of pipelines that aren't NER. So with all of those switched off, so we've only got the named entity recognition one still turned on. Then for the specified number of training iterations, so I specified 100, we're going to do this in a for loop. The first thing I'm going to do is randomly shuffle the training data. So remember I imported random. I can use the shuffle method of random and pass in the training data. And what that basically means is it'll shuffle up the sentences, which can be important when you've got lots and lots of data. Now, it's going to be almost redundant here because we've only got 2 sentences that we're training it with. But it's still good practice to do this because if you've got more data, which you will have in real world scenarios, then you're going to want to shuffle it. So it's best to always do that anyway. We're then going to set up a dictionary to store losses. Now, remember when Mike and I talked about losses in neural networks, so basically a loss is a summation of errors between your training and validation. So if, the lower the loss value, the better, because you've got lower amounts of error in the neural network. And that's what it's trying to minimize, its losses. So we've got a dictionary set up to record that. We then need to batch them up in the format SpaCy needs. Again, don't worry too much about that. I've put in some links if you want to read the technical details of why you do it in this particular way. But I'd recommend, at least initially, don't worry about this. Basically, all you're doing is you're batching up your data. Remember, we talked about neural networks. You have to sort of convert everything into numbers, and then you sort of batch it up and you send batches through. You don't send it all through at once. You send the data through in batches because it trains much better and it avoids overfitting. This basically is a built-in function into SpaCy that does this for you. And so if in doubt, just copy and paste that for a minute. Then for each batch of data in our batches, we're going to use something called zip, which basically joins the text with the annotation. So the text is our sentences, and our annotation is the label character position stuff that we're plunking in. So we're saying this is there's an organization at character 5 ending at character 11. And it joins that back with the sentences. Again, don't worry too much about that. Just know that's a line of code you need to deal with. And then we call to do the training. We just call this method here, which is the update method on the language, and we pass in the text that we want, so the sentences, the annotations, which are the named entities. So we're saying here are the sentences, here are the named entities. Here's the dropout rate. Remember when we talked about neural networks, we said that you have you often have dropout layers now, which is basically where the neural network randomly drops a percentage, switches off a percentage of your nodes to try and reduce overfitting. So it switches things off, so it doesn't get too well trained on the training data and become too specific to that. It just randomly drops things out, and it's really effective at reducing overfitting. And a 50% dropout seems high, but that's a pretty standard dropout rate. So basically, on every run of the neural network, half of the network will be switched off, and it'll randomly pick which 50% will be switched off. And then losses equal losses just basically means store the losses, i.e. the record of how close you are to what the actual value is in our dictionary called losses. Because remember, what it's trying to do is it's trying to train, so it's going to try and adjust the neural network so that it picks up when it sees the word pen cord in a sentence, that it's going to come out with a prediction that it's an organization. Because at the moment it's predicting that it's a geopolitical entity. And we want the same for system dynamics. We want it to pick out that it's to learn that and adjust itself such that when it sees system dynamics, it predicts that it's a named entity of type work of art. So once it's done that for all the batches, we can then print the losses. That'll give us an indication of how well it's performed. And then we can save this model, this trained new model, to disk. and we can just use this .toDisk method to do that. And so what that'll do, that saves an enhanced version of the NCore WebSM model. So the NCore WebSM model is the pre-trained model we use at the start. What we've done here is we've taken that model, we've opened up the bonnet, we've shoved in some new examples, and then we've got it to train on those new examples, saying, can you recognize these things as well? So it tries to improve itself, and then we've saved that. So that's now our new model that we can use. And we save that so that if we then come back to it after, in a new session, the next day or whatever, we can just load that model back up. We don't have to worry about going through and training it all over again. Now, the training will be pretty quick on this because we're only training 2 sentences. But if you're doing thousands and thousands of sentences, you probably want a much longer training, so it will take a lot longer to get to where it needs to be. So now we've trained the model, we can then test it, and we can see how well it performs. So first of all, we'll give it the sentences that we used to train it, because hopefully it'll pick those up. So these 2 sentences up here, hopefully it'll now say that Pencord is an organisation and Dan Chalk is a person. And we'll see how well it performs there, and then we'll test it on some new sentences that it hasn't seen. So Dan Chalk recently built a system dynamics model. That's a new sentence, but it contains these new things, new entities we've taught it. Pencord is lucky to have Mike Allen as one of its modelers, and Dan Chalk and Mike Allen build system dynamics models for Pencord. These are all new sentences, it hasn't seen those. So how well will it perform on picking out the named entities correctly, because they're in different positions than they were before as well. So let's run this and see what happens. So here we go, here's it training, and it's done it very quickly on my computer. So before, let's scroll all the way up. So before, remember, it was picking up Pencord as a GPE, which is wrong. So that's before the training of the existing pre-trained model. It then goes through the training, and you can see here, this is the loss values, the lower the better. So you can see it's gradually getting, there's a bit of fluctuation, but it's gradually getting better and better. So it's getting, it's being right more of the time in the way it's adjusting. Then we test it on the sentences it's already seen for training. So let's, and we'd hope it would get these right because it's just trained on them. So assuming the training's gone well, hopefully it'll pick it up. So on the sentence, Mike Allen loves system dynamics, it's picked out 2 sentences, 2 named entities. It's picked out Mike Allen as a person and system dynamics as a work of art. Fantastic, that's what we told it to do. Second sentence, Pencord's a fantastic team because Dan Chalk is in it. Picked out Pencord as an organisation and Dan Chalk as a person. Brilliant. So it's worked on the training sentences, although that's a fairly shallow victory because it's trained on that. It's very easy to get something to learn, a neural network to learn based on only the training sentences. So how well does it do on the new sentences, these new sentences that contain these new words that it's been shown, but in different sentences? So if we have a look, Dan Chalk recently built a system dynamics model. It hasn't seen that sentence before, but it has correctly picked out Dan Chalk as a person and system dynamics as a work of art. Similarly, Pencord's lucky to have Mike Allen as one of its modelers. It's picked out Pencord as an organisation and Mike Allen as a person. Remember, it was picking out Pencord before as a geopolitical entity, and I believe system dynamics, if you run it on the default model, gets picked out as an organisation, I think. And Dan Chalk and Mike Allen built SD models for Pencord. Again, it's picked out all 4 named entities there, and it's picked them out correctly with the correct. And so then, if we now apply our newly trained model back to our enhanced Trump article, which is the same as the original Trump article, just with the thing about Pencord added in, you see now it's picked out Pencord as an organisation. So we've trained our model, we've enhanced this core training model to now recognise that Pencord is an organisation. And that's how you do it. That's how you add in the training. Now, in reality, obviously, you would have much more than a couple of sentences that you're going to be adding in. You'll be adding in thousands. And the exercise that we may not have time to do, because it's 4 o'clock, but the exercise that I'd like you to have a look at will show you how you can do this on many more examples. Let me, just before I go on, are there any sort of questions about any of that?
It could be that I missed it in there somewhere, Dan, but when you put your test sentences in, is there a risk that it will, or your, you know, your first training stuff, is there a risk it will just not see them because it only picks half, or does it pick half of its data and everything you put in as well? So if we put in 1,000 things, would it take all of them?
Oh yes, so it will take all of them.
And it wouldn't dump any of them?
No. So what it's doing, the
Right.
dropout, basically what it's doing, it converts all the words into numbers, and
Yep.
it shoves through batches of these numbers, and they're basically going through these nodes, and all the nodes are doing are basically multiplying each incoming number by a weight.
Yep.
And that's basically where the magic of the neural network happens. What the dropout does is at each stage of the training, it randomly switches off half of those nodes, and that basically it stops it overfitting. So it's not the data that's being lost; it's the system that's trying to train, basically. But
it will take everything you put in as your training. It'll take 100% of that.
Yes. Yeah. Absolutely.
Right. Yeah. Okay.
Any other questions?
I noticed it's saying that Georgetown University is a work of art in the latest one that you've run.
Oh, well spotted. I hadn't spotted that. Right. Let's see what it said before. I'm guessing it was correct before.
Well, it's saying org on mine, so...
Yeah, org, right. Okay, so that's actually demonstrated a really nice example. So what we've done here is we've got it successfully. Yay, we've got it successfully to train that Pencord is an organization and System Dynamics is a work of art. But in doing so, it's now erroneously learnt, it now thinks that Georgetown University is a work of art because it's seen something in the pattern of the sentences that we gave it that is similar to the pattern that got it to see that Georgetown University is an organisation, and it now thinks that Georgetown University is a work of art. Now that demonstrates why you've got to be very careful about additional training and why you tend to want to do lots and lots and lots of examples, because if you just train on a few example sentences, you can knock something off balance, which is what's happened here. So you've gained something, but then you've also lost something here as well. Because you've only given it essentially one sentence example to show it what a system dynamics is a work of art, and it's having to base its training on that one example, and then it's learned something that is clearly good enough that it picks up system dynamics as a work of art, but then it's learned an erroneous link, and it now associates Georgetown University as a work of art as well.
So if you'd added the bit in about Pencord in that article somewhere different, or in a different article, it would have probably decided that Pencord wasn't a GPE, but was something else.
Possibly, it depends on it's the words that it sees before and after it.
So it could have thought it was a name or a person, or
so it might have thought it was something
depending on where we'd added it in.
And that's why you'd want to give it lots of different examples, because we've only given, in the training for System Dynamics, for example, and for Pencord, we've only given it a single example of where it would see that in a sentence. But essentially it needs to see that lots of times, see, okay, I see it in this kind of sentence, but I also see it in this kind of sentence and this kind of sentence. So it needs to see hundreds, thousands of these examples to get significantly better and to avoid things like this happening. So well spotted, Heather. I didn't notice it had done that, but that's a good example of why you've got to be careful about doing minimal additional training. Okay, so there's no way you'll finish this exercise because it was supposed to be an hour. Well, originally I had to tone it down because it was so brutally difficult that I realised it was completely unfair. So I've toned it right down. It is much easier now than it was. You won't finish it because it was supposed to be an hour-long exercise, but I would like you to have a stab at it at starting it, because it'll get you thinking through what you need to do. So I'm going to put you into your room. So for the next 25 minutes, have a go at starting this exercise, and if you got a chance to finish it in your own time in your groups. just dropped my microphone. There we go. There we go. Basically, you've been provided with a new article that's taken from a recent news story about a pen called project, which is the file exercise2 article.txt. And I've also given you a CSV file called x2training.csv, in which the first entry of each row contains a training sentence, and then the subsequent columns give the named entities and their labels. So let me show you, because it'll be a bit easier to see. So if we open up, where's the, okay, so if we have a look at the CSV file, zoom in. So the first row in each, the first column in each row is basically a sentence, and then you have pairs of columns after that that basically say, in this sentence, computer modelling is a named entity and it's this type. Mental health services is a named entity and it's this type. And it does this for each sentence. Now, in the .py file, oh, sorry, here's the article. This is just basically taken straight from a recent news story on our website that was talking about a recent project. And, oh, no, that's the solution. What I want you to do, so what I want you to do is, given that CSV file and given that article text, I want you to write a program that applies named entity recognition to the text in this text file, exercise2 article.txt, using the default model first, so the ncall WebSM, and prints each predicted named entity along with its label. Don't worry about dealing with duplicates, just have them all printed out as we did in the very first example. Then I want you to get the program to read in data from the CSV file and use that to train and save an enhanced version of this model. So you're going to use those training sentences stored in the CSV file along with the named entities that are declared, and use that to then stuff into SpaCy to improve the training. And I'll let you read this because you probably won't get this far anyway, not today. But this will tell you how to do this. So basically take a copy of the row, store it in a temporary list, how you're going to basically read in from the CSV file the information you need, the training sentences and the named entities, and then how you'll go through that bracket nightmare of then having to stuff that information into the format that SpaCy needs, and then you stuff all of that into the SpaCy training pipeline for named entity recognition. A lot of that you'll be able to copy and paste. The new bit is this around the reading it in from the CSV, which you know how to do, and I've got some extra information there about how to best do this, and then to turn the read in information into the format you need. So have a go at starting this, even if you only get as far as just playing around with the first bit on the default model, which you'll be used to using by now. But have a go at starting it, and then if you do have any time certainly over the next few weeks, if you get a bit bored over Christmas, have a go at doing this, because especially if any of you are doing this named entity recognition stuff for your projects, this is basically what you'll need to do, and this will act as a sort of template for how you would read in more examples, then train it and then test it on those new examples. Except because, of course, we've already discussed the disadvantage of just having 2 training sentences. So we clearly need a way in which we can read in vast swathes of new training sentences. Now, be careful when you do this in reality, because, of course, for every training sentence, you're also going to have to manually tell it what the named entities are. Because to train it, you're going to have to tell it where they are and what they are, which means if you've got 10,000 training sentences, fantastic. you're going to have to go through 10,000 sentences and tell it where all the named entities are. So you may want to just think about how many you're going to use to train, but you do need more than 2. So you need a decent amount of extra data for something that's manageable, so that either yourself or you can coax somebody into doing it can go through each sentence and pick out the named entities. So I'll break you into your breakout rooms now, just for the last 20 minutes, just have a go at starting this, and at least have a look at the first bit using the default model. And then when you get some time, especially if you're looking at NLP for your or named entity recognition, I'll just say for your projects, you may want to do this, because it'll be a good practice for what you're going to do. You'll probably also want to reread the comments on the program that about the stuffing it into the right format for SpaCy. You'll probably need to read that several times, because it's not nice. But I would also recommend, if you are doing this for your projects, to take the initial pain of writing a generic function that will do this for you, and then you can just use that function throughout your project. You'll write a function where you'll pass it a CSV file, and out the other side will pop the data in exactly the format SpaCy needs, and then you can just dump it straight into SpaCy. That will make your life a lot easier if you do that. And it goes right back to when we started talking about functions, about why you'd want functions. Great. Okay. So I'll split you into groups. Have a start at this for 20 minutes, and sort of have a chat about that, and have some fun. And if you're coming along to these, I'll drop in and out of the rooms. But if you're coming along on Thursday, I'll pop up some information later about the stuff for Thursday's session on sentiment analysis, which I know a number of you will also be doing for your projects. Great. Okay, let me stop the recording.